Hey, welcome back, and this is question 2.8 now, and it's called loop detection. So if you already took a look at the question and you're kind of confused by it, that's okay. It's actually an extension of a very famous problem that is still quite challenging. And it was actually solved by a professor, um, and it's very famous, well-known algorithm, so I couldn't imagine you actually deriving it during an interview, but it's kind of, it could be kind of expected for you to know because it's a very valuable tool to have. And that's because we want to be able to detect, if there's an infinite cycle in our linked list. And, that can happen a lot when dealing with linked lists or with graph algorithms. So it's a useful thing to know. And so this is an extension of that problem because not only do we want to detect if there's an infinite cycle in our linked list, we're also trying to return the node that's at the beginning of that loop or that infinite cycle. So I drew out two different linked lists here. And so you can see here that they both have an infinite loop. So if this pointer is iterating through this linked list, it would then enter this cycle and it will never leave because it's not a doubly linked list. We can't, be at this node and then hop back to its parent, or one of its ancestors. It's caught in here forever. So this would be a cycle. We would expect our algorithm to return true that, we have found a cycle in this linked list. And that's also true with this linked list, where if you're iterating through here, you could be caught within this infinite cycle. It's going to keep returning to the node 3 here. You could also have if I just drew one here, loop back to itself. It doesn't have to be necessarily to another node. And I know that it describes it as a circular linked list, but it doesn't have to have nodes that form a circular formation. It's more about, this cycle or this infinite loop that's, within your linked list. And so, yes, that's the linked list here. And now what we're going to want to do is return the node that's at the beginning of the loop. So we're not just returning true or false. Yes, there's a cycle. No, there's not a cycle. We're also wanting to return this node here because that's at the start of this infinite cycle. If we're dealing with this linked list, we would want to return this node because, it's the first node in this infinite loop. It's what we're, returning to and then iterating back. So that's the extension to the problem. Now, I'm going to take it kind of into two steps. First, we're going to, check if there's even a cycle, in our linked list. And that's a typical question for this when you're dealing with, loop detection. And then after that, once we detected, yes, there is a cycle, we'll find out how we can actually calculate this node here. Okay? So what I did is I just created 4 nodes here and I linked them together in the same way that we have this relationship here. So we have 4 nodes and the 4th node links back to this 3rd node and it loops infinitely. And I'm just making use of this node class where you just define the value that's stored in this node, so the data that's being stored in the node, and then we just have a pointer to the next node in the list. Very simple. And then here is our method where we're going to store all our logic, and it's our to-do. And we're just calling this and passing in the first node in our list, the node 1, which is this one right here. Okay? So to do this and find out, first we want to find out, is there a loop or a cycle in my list? Okay, and this is a typical question. And the solution for this is to use Floyd's cycle detection algorithm. It's also called the rabbit and the hare problem, or Floyd's, rabbit and the hare algorithm. And that's because it uses 2 pointers, okay? The first pointer is called the, oh, I called it the rabbit and the hare. It's called the tortoise and the hare, which is like turtle and the rabbit. And so you have one pointer that I'm going to call it the fast pointer, and it's going to be pointed to the first node in our list. And this is, some people call the variable name the hare. And then we have a slow pointer, which is also pointing to the head in our list, and it's called the tortoise, but we're just naming it the slow pointer for now. And what we do is, just like most linked list problem, is we're just going to iterate sequentially through this list. So the reason why we call the fast pointer the hare, the reason why it's fast in nature, is because with each iteration in this while loop, it's going to move 2 times. But the tortoise, with each iteration, is just going to move once, okay? So the hare is twice as fast as the tortoise. So I'll just write that out here. So fast pointer is equal to the fast pointer dot next, and the slow pointer is just equal to itself dot next, right? And so we're going to make our condition while the fast pointer does not equal null, and the fast pointer dot next does not equal null. So we don't want, us to perform this dot next operation on a null. So we do this check first, and we're just making sure that, if this is really a cycle that we're dealing with, like, this should never really equal null. Like, otherwise, if it did hit the end of a list and it does eventually become null, like, that means that we're not dealing with a cycle. And so we're actually just going to have this check here, so that if we exited this loop, if the fast pointer here does actually equal null, or the fast pointer dot next equals null, we're just going to return null here. And I actually should change this to node, because we're going to be returning a node here. And if we were dealing with a Boolean, we would just say, okay, this is false, because clearly there's no cycle. If we're just doing this first step of, is there even a loop in our linked list, we'd say return false. And what we do to check if there is actually a cycle in our list is if the fast pointer is equal to the slow pointer, we're going to break, and we would return true here, right? So if they both hit the end of our list, then, and they're both null, like, we just return false, because clearly it's just a straight linked list and there's no cycle in it. But what this means here is, if there is a loop, then with each iteration, the fast pointer is going to be one step closer, right, with each iteration. And that's because it's going twice as fast. So if we're caught in this loop, and one of them, I'll just kind of show it here. So if this is moving twice as fast, and this one, I'll grab my pointer here, is just moving one at a time, and this red one is moving, 2 at a time, it'll inevitably catch up, because, and with each iteration, this red one is going to get one step closer to the blue one. Okay, so it'll catch up, and if it does, then, and they're not equal to null, then you found a cycle in your list. So that's kind of the typical problem of, is there even a cycle in my list? So because we want to be returning a node, I'm just going to set this to null. So we'll return null if there is, if it's not a cycle. And here we're just going to continue if, we did actually find a cycle. So continue if we found a cycle. And so from here, we will, I'm just trying to think for a sec. We're going to say, okay, so, what is the distance when they equal each other? At what point in this cycle will they be, right? And so actually, if we kind of bring these back here, because the red one is going twice as fast as the blue one, this one, say if the blue one reaches this point, right? And I kind of said K. So K is the distance of the non-cycle part. Then the red one will have moved to K, but it's moved through K twice. So it's going to be 2K, right? Because, if this one moved twice, then the fast pointer has to have moved at least double that, right? So it would have moved to this point. So we can say that, okay, when this one is at the start of the loop, the fast pointer is, at this equal to the distance that it would have traveled into this loop. And so because they, catch up at a rate of 1, so, this one moves twice as fast in this infinite loop, and this blue one moves just one iteration at a time, but each iteration, they're getting one step closer, okay? And so they're gonna actually collide at the length of the loop minus K, right? I'm just gonna write that out here. So their collision is equal to the, size of the loop or the length of the loop minus K, because this one will already be K iterations into the loop, right? And so they're going to be actually right here when they collide, right? Because this is 2 and this is the distance of 2. And so what we're going to do is, because we know that they're colliding at this point, right? So right here, when they're colliding, this is going to be a collision of size loop minus K. That's the node that they've collided at. So what we do is we actually just reset the slow pointer to the head of our loop. Right, so we just set this blue pointer back to the very beginning. And why is that? Because we want to return this node here, the start of our loop. And the way that we find this is that because we know we are currently, I'll just write it out, K distance from the start of our loop, right? Then why don't we just set this blue pointer, our slow pointer, back to the very beginning, and then we'll just iterate them one at a time, and then they'll eventually just hit the, start of our loop, and then we'll return that. So I hope that made sense. You might have to slowly digest it a little bit, but I'm going to go ahead and implement it. I'll definitely recommend just pausing it, kind of rolling in your head a few times, and then kind of continuing this video. So what we're going to do is, while the slow pointer does not equal the fast pointer, we're going to iterate. So slow pointer is equal to slow pointer dot next, and fast pointer is equal to the fast pointer dot next. And then we just simply return either of these because we're equal to each other. I'll just say the slow pointer. Great, and so I'm just going to run this algorithm here. We might have an error too. Oh, no errors. Great. And so it returned the value of 3 here. And if you look back here, that's exactly what we would have expected because, well, it's looping from 4. We just look at this one again, back to 3, and that is the start of our cycle. And so say if we change this so it loops back to itself. So node 4 is now looping back at itself, and we run this. It then returns 4, and that would look like something like this. 4 is just looping right back at itself. So we would expect to return, I'll mark it in green this time, expect to return 4 because it's at the start of the loop. That's exactly what we got. So yeah, this performance is O of n, and that's just because we're going to be iterating through our loop, and it might be a few times or such, but it's just going to be some constant of n or multiplied by n, and we have a space complexity of O of 1, and that's because we're not using an array or a hash map. We're not really dealing with any extra data structures other than just 2 pointers iterating through our list. So I hope that helped, and good luck with the rest of your algorithms. I appreciate you guys stopping by and watching the video. Have a great day.